Hey there, and welcome. Have you ever just looked around and wondered what holds everything together? I mean, seriously, the phone in your hand, the air you're breathing, the stars, what's the glue? Well, today we're diving into the invisible forces that make everything, well, everything. We're talking about chemical bonds. So let's just start with the biggest, most fundamental question there is. Why isn't the universe just a floating soup of disconnected atoms? What makes a grain of salt, salt, or a drop of water, water? Turns out the answer is way simpler than you'd think, and it's the engine that drives all of chemistry. And that's it. One word: stability. You know, atoms are kind of like people. They just want to be in a comfortable, stable, low-energy state. And for most atoms out there, being alone is actually super stressful and unstable. They need to connect, to bond, to find that sense of chemical peace. And that kicks off our first big idea, this epic atomic quest for stability. It's a journey that explains pretty much every single chemical reaction you could possibly imagine. So here's the deal, the fundamental problem that almost every atom faces. Think of their outer layer of electrons like a puzzle with missing pieces. It's incomplete. This makes them unstable, super reactive, always looking for a way to fix the situation. Their one and only goal? To get a full outer shell. Just like the noble gases. Those are the rock stars of the periodic table, perfectly stable and totally content. Okay, so how do they solve this puzzle? Well, the first solution is what we call an ionic bond, and it's a really straightforward but incredibly powerful strategy. One atom gives and another one takes. And this is the core idea right here. It's not a loan, it's not a share, it's a complete 100% transfer of an electron. It's a giveaway. This usually goes down between a metal, which is practically dying to get rid of an electron, and a nonmetal, which desperately wants one. I absolutely love this analogy. Just picture it. One atom has a lunch it doesn't even want, and another atom is starving. So the first one just gives the entire lunchbox away. Done deal. That complete, no-strings-attached giveaway, that's the heart of an ionic bond. So let's look at the most famous example of all time, table salt, or sodium chloride. Sodium has this one annoying extra electron in its outer shell. It just wants it gone. Meanwhile, chlorine is so close to having a perfect set, it's just one electron short. I think you can see where this is going. And boom! Sodium just hands over its unwanted electron to chlorine. In that one simple move, both atoms get exactly what they wanted. Both now have stable, full outer shells. Problem solved. Everybody's happy. But wait, here's the magic part. After that transfer, the atoms aren't neutral anymore. They've become charged particles we call ions. Sodium, having lost a negative electron, is now positive, and chlorine, having gained one, is now negative. And what do we know about opposites? They attract. That incredibly powerful magnetic-like force that's now pulling them together, that is the ionic bond. Okay, but what if giving and taking just isn't an option? What if no atom is strong enough to just snatch an electron from another? Well, that brings us to the second major solution for stability, sharing. And this is what we call a covalent bond. The key word you've got to remember here is mutual sharing. This is a partnership. Instead of one atom winning and one losing, they decide to cooperate and share their electrons to solve their stability problem together. And of course, there's another great food analogy for this one. Imagine one friend shows up with just the bread, and the other has just the potato filling. Neither one has a full meal. So what do? They put their resources together, they share, and now they both get to eat. That's a covalent bond. It's a team effort. You can kind of picture how this works, right? The electrons from one atom start to orbit around the other one too. They create a new, bigger system where they're shared between them. And by doing this, each atom gets to count the shared electrons as its own. It's a clever loophole that gets everyone to that stable, happy state. And this isn't some abstract chemistry concept. This is the bond that literally holds together the most important molecules for life. The water you drink, the methane and natural gas, all of it is built on the simple power of sharing. So, okay, we have these two major types of bonds, giving and sharing. Why does it matter? I mean, who cares? Well, it matters because the type of bond an atom forms determines pretty much everything about the world we can see and touch. Let's just break it down. That super strong magnetic pull in ionic bonds, that's why salt is a hard, crystalline solid that you have to heat up like crazy to melt. But the attraction between covalent molecules, it's much weaker. And that's why things like water or CO2 are liquids or gases at room temperature. They can flow and move around. So what's the big takeaway here? It's that the invisible strength of a bond completely dictates the visible reality of a substance. A strong bond locks things in place, creating a rigid solid. A weaker bond allows for the beautiful flow of a liquid or the total freedom of a gas. It's all connected. All right, now for a curveball. A really fascinating special case. What happens when two atoms decide to share electrons, but one atom brings both of the electrons to the party? This is a funky little thing called a coordinate bond. It's kind of like a covalent bond, but with a twist. You start with one atom that's already stable but has this extra pair of electrons, a lone pair, just hanging out. Then, along comes another particle that's desperate for two electrons. The first atom generously donates its entire pair to form a new shared bond. It's a one-sided share, but hey, works. And this isn't just some weird, rare thing. This is how incredibly important substances get made. The ammonium ion, which is a vital part of the fertilizers that literally help feed the planet, is held together by this very special one-sided sharing bond. And so there we have it. When you boil it all down, those are the three fundamental strategies that atoms use to find stability, to connect with each other, and to build the entire world around us. It really does just come down to these three simple ideas: completely giving an electron away, taking one for yourself, or working together in a partnership to share. These are basically the social rules of the atomic universe. Which, of course, leaves us with a final thought. If the entire universe, from a tiny grain of salt to you and me, is built on these simple principles of giving, taking, and sharing, well, it makes you wonder about the connections we form ourselves, doesn't it? What's the best way to form our own bond?